Delaware Tech, Chemistry 100, Chemistry 110, Unit 6 continued, Charles's Law. Charles's Law deals with the relationship between volume of a gas and temperature of a gas. And what Charles, actually his name was pronounced Charles, he was Jacques Charles, but most people say Charles. Charles's Law deals with the relationship between gas volume and gas temperature, and what he found was that these two parameters are directly proportional to one another. So another way to say that mathematically would be that the volume equals some constant times the temperature. What that means, another way to say that would be that the volume divided by temperature is constant. That ratio of volume to temperature is constant. And what that means is if one of these two values goes up, the other will go up. If one of these two values goes down, the other will go down. If you heat something up, it will expand. If you cool it down, it will shrink. So temperature goes up, volume goes up. Temperature goes down, volume goes down. And while these two versions are mathematically correct, they're not very useful for your Charles Law problems that you're going to get. So another way to write this is by saying, since V over T is a constant, then that means any set of V over T will equal any other set of V over T for the same N and P constant values. In other words, if we keep the number of molecules or atoms constant, N is constant, and the pressure constant, the only thing that will vary is volume and temperature in this relationship. So let's look at how to use this in a formula. A fixed amount of gases initially has a volume of 8.3 liters and a temperature of 17 degrees Celsius. What is the final volume? If it is then heated to 96 degrees Celsius, pressure is kept constant. Well, there are a couple things you should note here right away. Number one, you should note that the values of temperature in Celsius and all gas law problems have to be done in Kelvin. So we need to convert both of those values into Kelvin degree temperatures in order to use them in our formulas. And as before, let's make a table. We'll make a table with our initial and our final values of our four parameters. We have pressure, volume, number, and temperature. We have our before state, we'll call number 1, and our after state, we'll call number 2, and we can start filling in. A fixed amount. This tells us that the number is not changing. It's sealed. Initial volume of 8.3 liters. We can fill that in, 8.3 liters. An initial temperature of 17 degrees C. Well, that will not do. We have to turn this into Kelvin. And how do we do that? By adding 273.15 degrees to get the Kelvin value. And if we add these together, we'll get 290.15 degrees Kelvin. Now, you might be wondering, why didn't we round this? Well, if this was the only question we were asking, what is the temperature in Kelvin, we would round it. But since we're solving for something else later on in the problem, we don't round until the very end. So we're going to put our number in now. 290.15 degrees Kelvin is our initial temperature. And we have a final temperature. It's heated to a certain temperature, 96 degrees Celsius. And we do the same thing. We add that to 273.15. Use a calculator if you can't do this in your head. And you get 369.15 degrees Kelvin. And we can put that in our table, 369.15 degrees Kelvin. I'll put the degrees down here. And then we also have that the pressure is kept constant. Okay, P1 equals P2. So that, we don't worry about those two things. So the only thing we need to know is the final volume, V2. So how do we solve for that? Well, I'm going to erase some of these notes here. We don't need to solve for that anymore. And you'll see it's built into the printed equation that I have coming up. But we start with Charles's law. V1 over T1 equals V2 over T2. And by the way, if you had to solve for something and it would be easier to solve for it the other way around, there's no reason you couldn't rewrite this as T1 over V1 equals T2 over V2. Those are the same formula just inverted. But what I highly recommend you do is anytime you see a fraction in a formula, cross-multiply. Cross-multiply means you multiply the numerator on one side with the denominator on the other, and vice versa, and you'll end up with a formula that says V1T2 equals V2 T1, and this is much easier to manipulate algebraically. Now, since you're solving for V2 is very easy to solve. You just divide both sides by T1. T1's cancel on this side, and you're left with the equation that I have written here. So I'll erase some of these extraneous notes here, some of these underlines, and this will leave us with the important part, our table and the final form of the formula. And now we can start plugging numbers into our formula. Another thing to be careful about, by the way, is a lot of people don't realize when they're plugging in their numbers that they're no longer paired together like they were in Boyle's law. V1 is now paired with T2, and V1 is opposite of T1. So be careful where you place your temperatures. In this case, the final temperature is in the numerator, the top, and the initial temperature is in the denominator. So it's very easy to make this mistake. I can't tell you how many times I've made this very same mistake. So this is why it's a good idea to make your table and make everything clear and solve for your variable first. And now that you have your variables, you have your temperatures in the right format, you have everything in the right form, now you can actually go through and multiply your equation and get your answer of 10.560 liters. Now, at this point, you look at your original problem, and you can see that we have various values, 2 significant figures, 2 significant figures, 2. So our final answer must be rounded to 2 sig figs, so 10.560 becomes 11 liters, and that would be our final answer for this problem. And then I'll delete these notes here. So when you're finally finished with the problem, ask yourself, does this make sense? We used to have a volume of 8.3 liters. It was cool. And then we heated it up. What happened to the volume? Well, the volume went up. Does that make sense? Well, yes, it does. When we heat something up, the volume will increase. Let's look at another problem. What is the temperature of a fixed amount of gas that is expanded from 2.5 liters at 25 degrees C to 4.1 liters, all done at constant pressure? Well, again, we're going to make our table. We have our before condition, we have our after condition, P, V, N, and T. It's fixed amount, it's a sealed container. Those two are equal. The pressure is constant. Pressure 1 is equal to pressure 2. Our initial temperature is 25 degrees C. So we need to turn that into Kelvin. If we add 273.15 to that temperature, we will get our value of 298.15 degrees Kelvin. Don't round yet. And we have our initial volume, 2.5 liters, and we have our final volume, 4.1 liters. So the only thing we're missing is T2. So I'll erase some of these notes here. And now we pull out our Charles's law equation because all we're dealing with is V and T. And we've got a little overlap here. I'm going to get rid of the pressure so that's not in the way of our calculation. Just put 1 and 2 back here. And we have a formula. Now, again, if you cross-multiply first, it'll make solving for T2 much easier. You'll end up with V1 T2 equals V2 T1. This is what you're solving for. Divide both sides by V1. V1's cancel, and you're left with your final version, which is right here. So I'm going to erase those notes that I just created here. And we're not really worried about N, so you can just keep that on the side. The only thing we're worried about is the volume and the temperature at this point. So now we have our formula, and we have our temperature in Kelvin, and now we just fill in the numbers, making sure that we put the right volume in the right place, and we only have one temperature here. we plug this in, and we end up with a calculation saying that our initial answer is 488.97 degrees Kelvin. But if you're given a problem where they give everything in Celsius or centigrade, Celsius and centigrade are the same thing. Anders Celsius created the centigrade scale, so they mean the same thing. You then have to reconvert that back into Celsius or centigrade. By subtracting the 273.15, you get your answer, and then you would round to the nearest degree or to two significant figures, depending on what I tell you, because with temperature it's a little more complicated, so I'll say what to do it to. In this case, we could either round to the nearest degree, which would be 216 degrees Celsius, or to two significant figures, which would be 220 degrees Celsius, and that would be our problem. And I'm going to erase the rest of the notes, and that's it for Charles's law.